All right, let's dive in. Today, we're going to crack the code on a world that is literally all around you, but almost completely invisible. I'm talking about embedded systems. You know, those tiny, dedicated computers that are hiding inside everything from your car's airbags to the traffic lights on your street. And trust me, they play by a completely different set of rules.
So let me start with a question, a puzzle really. Why is it that the systems where failure is just not an option? I mean, think about medical devices or the anti-lock brakes in your car. Why do they often run on processors that seem, well, ancient compared to what's in your phone? It just feels totally backward, doesn't it?
Well, it all comes down to the stakes. A desktop PC, it's got gigabytes of RAM. If it crashes, who cares? You just reboot it. But an airbag controller, that little thing might only have a few kilobytes of RAM, and the cost of failure is catastrophic. You see, this isn't a race for speed. It's a relentless demand for perfection inside some incredibly tight limits.
And that leads us to the one principle, the one golden rule that governs every single decision in this entire field. It's all about fighting two big enemies, overhead and non-determinism.
Okay, so first up is overhead. In a system that's only got kilobytes of RAM to work with, every single byte matters. C++ features that we take for granted on a desktop, things that seem free like virtual functions or dynamic memory, they can eat up precious resources that we simply do not have. Every single byte has to justify its existence.
Second, and you could argue this is even more important, is non-determinism. What's that? It's basically any behavior that you can't predict down to the microsecond. For an airbag, we don't just need the right answer, we need it at the exact right time, every single time, without fail. In this world, predictability is king. It's valued way more than just raw speed.
And the first major casualty of this golden rule, it's what sparks the great debate between C and C++. It's a choice that perfectly shows you the kind of trade-offs we're talking about here.
You know, C is often the language of choice in these really deep, hardcore embedded systems, for one simple reason. It is incredibly direct. The code you write maps very, very closely to the machine instructions the processor is actually going to run. There's no hidden magic, no runtime surprises. As the old saying goes, what you see is what you get.
So this brings us to a perfect example. Why would a really powerful C++ feature, like a virtual function, I mean, it's essential for a concept called dynamic polymorphism, why would that be a huge red flag in a safety-critical system? It's because it smashes our golden rule to pieces, introducing both hidden overhead and non-determinism.
See, a direct function call in C is just a single, predictable jump for the processor. But a virtual call, oh, that's a whole different story. It's a multi-step scavenger hunt. The CPU has to follow a hidden pointer, then it has to look up the function's address in a special table, and then it can finally make the jump. Each one of those steps adds a tiny, unpredictable delay. And in a real-time system, that is the enemy. Now, this whole mindset of predictability over everything else, it applies directly to our next big topic, memory management. You can't just ask for memory whenever you feel like it.
If you're coming from the C++ world, you'd use new and delete all the time to dynamically allocate memory. But in a ton of embedded projects, those keywords are completely 100% forbidden. So why? Because they lead to what I like to call a slow, creeping death for any system that has to run for years on end without ever rebooting.
The problem has a name. It's called heap fragmentation. Imagine this. Over time, as your system grabs and releases blocks of memory of all different sizes, the available free space gets chopped up into thousands of tiny, unusable little pieces, just like you see here. And here's the punchline. Your system might say, hey, I've got 100 kilobytes of free memory, but if there's no single continuous chunk that's at least 1 kilobyte long, your request for a tiny 1 KB buffer will fail, and your whole system will crash. That is just not an acceptable risk. Period. So, what do they do instead? Well, embedded developers use memory patterns that are super predictable. They pre-allocate everything they can up front. For global variables, in these sections called .data and .bss, and they use the highly predictable stack for local variables. And the heap, that chaotic source of non-determinism, yeah, that's avoided at all costs. So we've seen how we have to avoid unpredictable code and unpredictable memory. But that discipline, that rigor, it allows us to do something truly remarkable. Control hardware directly, right down to the bare metal. Let's see exactly how that works. In fact,
We're about to break down what many people call the #1 interview question for anyone who wants to become an embedded engineer. And it's because it tests everything we've just been talking about.
Okay, here's the scenario. You're told there's a hardware register that controls an LED, and it lives at this specific memory address. Your job is to write a single line of C code to turn on the 5th bit of that register. And this is the answer. I know it looks terrifying, but it's actually beautifully logical once you see how it works.
Let's just break it down piece by piece. First, we take that raw number, that address, and we tell the compiler, hey, treat this number as a pointer to a 32-bit integer. Next is that volatile keyword, which is super important. We'll get back to that in a second. The little star in front lets us dereference the pointer, which basically means we can now access the value at that address. And finally, this little bit of bitwise logic flips bit number 5 to a 1 without messing up any of the other bits.
And that volatile keyword, it is absolutely positively critical. It's a direct message to the compiler that says, hey, the value at this memory address can be changed by hardware at any moment, so you are not allowed to get clever and optimize away any of my reads or writes to it. Seriously, without this, your code might just not work at all.
Okay, so let's zoom out for a minute. This whole philosophy, this constant battle of determinism versus features, it doesn't just apply to a single line of code, it applies to the entire architecture of the system.
Take, for instance, the choice between an RTOS, that's a real-time operating system, and something like Linux. An RTOS is built for one thing and one thing only: determinism. It guarantees that a task will meet its deadline. Linux, on the other hand, gives you incredible features, right? Networking, file systems, you name it, but it makes absolutely no timing guarantees. The RTOS is your airbag controller. Linux is your car's infotainment system.
And this thinking goes even deeper, right down to how tasks are managed. Linux uses these heavyweight things called processes. Each one lives in its own protected memory bubble. It's great for stability. If one app crashes, it doesn't take down the whole system. But in RTOS, it uses lightweight threads that all share the same memory. It's way faster and more efficient, but it demands a lot more discipline from the programmer. It's a classic trade-off. Do you want isolation for safety or shared access for predictable performance?
And what's really cool is that this software choice is mirrored right there in the silicon, in the hardware itself. A little Cortex-M microcontroller, the kind you'd find in an RTO system, has a simple memory protection unit, or MPU. Think of it like a basic firewall between tasks. But a big Cortex-A application processor, the kind that runs Linux on your phone, has a full-blown memory management unit, or MMU. That's the powerful hardware that lets it create those isolated memory bubbles. The hardware itself is purpose-built for the philosophy.
So we end up right back where we started. In the high-stakes world of embedded systems, where a single missed deadline can be a catastrophic failure, the best technology isn't always the fastest, or the one with the most bells and whistles. It's the one that is the most boringly, reliably, and beautifully predictable.